Hi everybody. So now we're gonna move on to chapter 14 and 15, and we're also gonna do these together, both 14 and 15. But first, let's start with the terms for chapter 14. So this is a new section now, so new terms. So the first one is gonna be temperature. That's gonna be a capital T. And it has different units, degrees Celsius, degrees Fahrenheit, and also a new one called kelvins, capital K. These are all going to be units for temperature. Next is going to be a term heat. The variable is going to be capital Q. Again, different sets of units. Heat can be measured in joules because it's a form of energy. Also measured in calories. Even in BTUs, British thermal units. Next, also, we're going to have time. That's going to be a lowercase t measured in seconds. Area, capital A, measured in square meters. Length, L, measured in meters. There's a new term, thermal conductivity. And that one is a lowercase k. And the units are going to be joules divided by meter second degrees Celsius. And mass, M, measured in kilograms. Another new term, specific heat. That's going to be a lowercase c, measured in joules per kilogram per degree Celsius. And the last one is going to be latent heat. And the variable for this one is going to be a capital L. Actually, let me make length then so we don't get those confused. Length will be a lowercase l, and latent heat is going to be a capital L, measured in joules per kilograms. And let's look at the formulas for this chapter. Temperature in Fahrenheit is going to be 9/5 temperature in Celsius plus 32. Temperature in kelvins is going to be 273.15 plus temperature in Celsius. The rate at which heat flows divided by time is going to be conductivity multiplied by cross-sectional area multiplied by the temperature on the high side minus temperature on the low side divided by length. Heat is going to be mass times specific heat times change in temperature, and heat is going to be mass times latent heat. So these are the formulas that we're going to use and the terms that we're going to look at for chapter 14. So now we're going to do the lecture for chapter 14, and I'm going to break this up into I think about 3 videos because it's going to be pretty long. So the first one is going to be the first page in the lecture that deals with temperature scales. Okay, so let's start off with a computer simulation to see what temperature is. So here you have a container with a gas, and down there you see that it says it's cold. So let's see what happens if you heat up or increase the temperature. If you notice, as the temperature rises, it moves faster. And that's the basic idea. Temperature just tells you how fast atoms move inside of a gas. So that's going to be our first description. I guess I'll do this one. So let's say that you have 2 gases. One of them is going to be a cold gas, And in this case here, there's going to be gas atoms, but they'll be moving around pretty slowly. So just kind of like that. And relatively, if you have a hot gas also, so this is cold. And if you have a hot gas, so here, the gas atom that's over here is going to be moving really fast, so it'll have a high velocity that'll take it to the other end. Here also, this gas atom is going to be moving really fast, be able to travel to the other end. And in general, the gas atoms are going to be moving around faster because they're hotter, or they have a higher temperature. So that's what temperature is. Temperature capital T is a description of the velocity of the gases, the atoms inside of a gas. And there's a couple of different temperature scales. There's the Celsius scale, I'll do it over here, Celsius scale and a Fahrenheit scale. And you can convert between the two using the next formula that I'm going to show you. So the temperature in Fahrenheit is defined as 9/5 times the temperature in Celsius plus 32. But there's another scale that has more of a physical meaning, and for that, let's look at this picture here. So you see that you have a hot air balloon, and the basic idea for the hot air balloon is that it's hot and it's big, so it has a large volume. So let's make a graph then of temperature versus volume. So this is going to be the volume here, and this is going to be the temperature over here, measured in degrees Celsius. And we're going to say that this is going to be 0 degrees Celsius. So a hot air balloon, it's hot. So also this is going to be the hot side, and then this is going to be the cold side. So a hot air balloon is going to be two things. It's going to be hot and it's going to be big. So a hot air balloon is going to be somewhere over here, really big and also really hot. And as you cool the balloon down, the balloon is going to start to flatten out. So as the temperature goes down, there's going to be a point where the balloon is going to get smaller. And if you get to 0 degrees Celsius, that's the temperature that water freezes. So there, the balloon is still going to be, take up some space. It's going to be pretty small. So there's kind of a trend here, and if you extrapolate the trend, what you find is that, is there a temperature? Well, here the temperature is 0. But the volume is still, here let's say the volume is 1. So it still has some volume. So is there a temperature where the volume does go to 0? So you can just extract this line back. And what you find is that there is a temperature where the volume does go to 0. And that temperature winds up being minus 273.15 degrees Celsius. And this is true for all gases. So because this temperature is true for all gases, meaning that all gases, whether it's air or helium or any other kind of a gas, its volume goes to 0 at that temperature. We're going to use this as a better temperature scale. And this temperature scale says that, so let me, I guess I can just erase this. So this is minus 273. So this new temperature scale is called a Kelvin scale. And it says that the temperature in kelvins is going to be 273.15 plus the temperature in Celsius. This simulation is going to help us to understand the Kelvin temperature scale and the idea of absolute zero. So you have two different kinds of containers. At first, on the right, you have a container that has a fixed volume, just a cylinder or gas tank, and the volume doesn't change. And you have a gas. You're looking at gas molecules inside this gas tank here. And a second container is what's called a piston, where the upper lid can move up and down here. But in both cases, though, what you're looking at is gas molecules on the inside of these containers. And so what we said before is that what temperature is pretty much, it characterizes how fast gas molecules move. So if you look at it both cases, the gas in both of these containers, they move at about the same speed. And the reason why is that they're both at about the same temperature. And as you increase the temperature, you notice in both cases that the gas molecules are moving faster. So again, the bigger the temperature, the faster the gas molecules move. And the lower the temperature, the slower the gas molecules move in both of these cases here. So again, what temperature is, it just tells you how fast gas molecules move. So there's a special temperature scale called a Kelvin scale. And what happens here is that here the simulation doesn't really show it to you, but ideally there should be a temperature where so here we're at the minimum temperature that we can reach on this scale here. So in this case, even though we're at the minimum temperature, there's still motion happening in both of these cases there. So to better describe what happens inside of, for atoms, we're going to introduce a new temperature scale called a Kelvin temperature scale. And in this Kelvin temperature scale, what happens is that at 0 kelvins, all motion is going to stop. So this simulation doesn't show you that here, but in this Kelvin scale is defined as at 0 kelvins, all motion stops.